The handwheel turned with the speed that only emergency brings. It was October 1889, and the forge line at Bellport Ironworks had just signaled a problem downstream, a rupture in a feed line, minor but urgent. The operator's hands moved without hesitation. 3 full rotations of the main steam shut-off valve, counterclockwise, firm and practiced. The wheel offered its usual resistance, then gave way as the stem began to close. Steam should have stopped within seconds. It didn't. The hiss continued from the pipe beyond the valve, quieter than before but unmistakable. The operator stood motionless, one hand still on the wheel, now fully closed, listening. 5 seconds. 8. The sound thinned but did not vanish. He could feel warmth radiating from the downstream flange, heat that should have been fading faster. 12 seconds after closure, the hiss finally stopped. He placed his palm against the pipe, still hot but cooling now. Silence settled over the valve station. Everything had worked. The valve was closed. The system was safe. But something had lingered, something that should not have been there. He wrote nothing in the log. There was nothing definitive to write. The valve had closed. The wheel had turned fully. The steam had stopped. There had been no failure, no alarm, no measurable defect. Only a delay that lived in the space between expectation and occurrence, a gap too narrow to name but wide enough to notice. Later that evening, in the ground floor maintenance office, he mentioned it to the night foreman. Not as a report, just an observation. The valve had been slow, not broken, just slow. The foreman nodded and said nothing. But 2 weeks later, during a planned shutdown of the same line, he stood near the valve himself and watched the operator close it. This time the closure was deliberate, unhurried. The wheel turned smoothly. The valve seated without incident. Steam stopped flowing within 3 seconds. The foreman made a note on his clipboard, but did not file a work order. It was only during rapid shutdowns that the delay appeared. By late November, 3 separate operators had noticed the same behavior. The valve in question was a bronze-bodied globe valve, 8 inches in diameter, installed in 1884 to isolate the main steam supply to the forge heating line. It controlled superheated steam at 90 pounds per square inch, a pressure well within its rated capacity. The valve had been inspected quarterly since installation. Its packing was tight, its stem straight, its seat smooth and free of scoring. On paper, it was ordinary, but operators began to recognize a pattern. During slow, controlled closures, when the handwheel was turned gradually over 15 or 20 seconds, the valve behaved exactly as designed. Steam flow decreased steadily, and silence followed closure within moments. During rapid closures, however, especially those initiated during transient conditions or emergency stops, the valve closed mechanically, but steam continued to flow for several seconds longer than expected. One operator described it as though the valve were catching up to itself. The delay was not constant. It ranged from 4 to 14 seconds depending on conditions that were difficult to isolate. Temperature, flow rate, and how quickly the handwheel was turned all seemed to influence it, but no single variable explained the behavior completely. What troubled the operators most was not the delay itself, but its subtlety. The valve never failed to close. It never leaked after closure. The handwheel never jammed. There was no mechanical breakdown, no visible wear, no audible grinding or chattering. It simply took longer than it should have for the steam to stop. The chief engineer, a man named Albert Grissom, was finally informed in early December. He arrived at the valve station on a cold morning and observed a test closure himself. The operator turned the wheel briskly, 3 rotations in under 5 seconds. The valve closed. Steam hissed from the downstream pipe for 9 seconds. Grissom placed his hand on the valve body, warm but not excessively so. He checked the packing gland secure. He examined the bonnet bolts, tight and evenly torqued. He opened the valve partially and closed it again, this time slowly. The hiss stopped within 2 seconds. He ordered the valve disassembled for inspection. The valve was removed from service on December 9, 1889. The disassembly took place in the main shop under adequate light. Grissom supervised personally, along with 2 machinists and the forge line supervisor. They worked methodically, removing the bonnet, withdrawing the stem, and lifting the disc from its seat. Every component was measured, examined, and compared against the installation drawings. The seat was smooth, with no pitting or erosion. The disc face showed even contact wear, a thin, polished ring that indicated proper alignment. The stem was straight to within 0.02 of an inch over its full length. The packing was slightly compressed, but intact, with no evidence of leakage or thermal damage. The bonnet threads were clean. The handwheel attachment was secure. There was nothing wrong with the valve. It was reassembled with new packing and reinstalled the following day. A test closure was performed under normal operating conditions. The valve closed smoothly. Steam stopped within 3 seconds. For 2 weeks it behaved perfectly. Then on December 28th, during a rapid shutdown caused by a pressure surge elsewhere in the plant, the delay returned. This time it was measured. 11 seconds between full closure of the handwheel and cessation of steam flow downstream. The operator noted it immediately. Grissom was summoned. He arrived to find the valve fully closed, the pipe cooling, and no steam escaping. He opened and closed the valve twice more under normal conditions. Both times, closure was prompt. He returned to his office and reviewed the maintenance logs for every valve of similar type in the plant. None had exhibited the same behavior. This valve, and only this valve, resisted closure during rapid, high-pressure shutdowns. The pattern was now undeniable. The delay occurred most consistently when 3 conditions aligned: high steam pressure, rapid handwheel rotation, and a sudden demand for closure. Under these conditions, the valve's mechanical closure preceded the cessation of steam flow by a measurable interval. Grissom began to suspect that the valve was not malfunctioning. It was responding to forces that only appeared during shutdown, forces that resisted closure without preventing it. A steam shutoff valve operates on a simple principle: mechanical obstruction of flow. In a globe valve, the handwheel drives a threaded stem downward, pressing a disc against a seat machined into the valve body. When the disc contacts the seat with sufficient force, the flow path is blocked. Steam stops. The system is isolated. The process is immediate and mechanical. Closure depends only on the stem's position, not on the pressure or state of the steam itself. Under ideal conditions, the time between the disc contacting the seat and the cessation of flow downstream is nearly instantaneous. Any steam remaining in the pipe beyond the valve dissipates within a second or two, escaping through open vents or condensing as pressure drops. This is what should happen. The valve at Bellport was designed to close in 3 full turns of the handwheel, translating to approximately 15 inches of stem travel. The threads were cut with a fine pitch to provide mechanical advantage, allowing an operator to generate several hundred pounds of seating force without undue effort. The disc and seat were lapped to ensure metal-to-metal contact across the full circumference, creating a seal capable of holding against 90 pounds of differential pressure. The valve's function was purely mechanical. It did not rely on pressure balance, spring assistance, or external actuation. The operator's hand, through the stem and disc, directly controlled the position of the closure element. This made the delay difficult to explain. If the disc was seated, if the handwheel had been turned fully and the stem driven downward to its limit, then the flow path should have been blocked. Steam should not have continued to flow. Yet it did, consistently, under specific conditions. Grissom began to consider that the delay was not a failure of the valve to close, but a resistance to closure that occurred in the moments immediately before and during seating. Something was opposing the downward motion of the disc, something transient, something tied to the steam itself. He requested detailed measurements of the valve's behavior during closure, the torque required to turn the handwheel, the position of the stem at each moment, and the pressure downstream of the valve as it closed. These measurements would require instrumentation that did not yet exist in a practical form, but Grissom believed the phenomenon could still be understood through careful observation and reasoning. The question was not whether the valve closed, it was why closure took longer than it should. In January 1890, Grissom conducted a series of controlled tests. He arranged for the forge line to be taken offline for a full day, allowing him to cycle the valve repeatedly under varying conditions while observers recorded the results. Pressure gauges were installed immediately upstream and downstream of the valve. A machinist stood beside the operator, noting the resistance felt in the handwheel during each closure. The first test was a slow closure, 20 seconds from fully open to fully closed. The handwheel turned smoothly. Downstream pressure dropped steadily as the disc approached the seat, reaching zero within 2 seconds of full closure. No unusual resistance was noted. The second test was a rapid closure, 5 seconds from open to closed. The handwheel turned with more effort in the final rotation. Downstream pressure dropped, but more slowly than expected. Steam continued to hiss from a vent valve beyond the shutoff for 8 seconds after the handwheel stopped turning. Grissom repeated the rapid closure 3 more times. The delay persisted, ranging from 6 to 10 seconds. In each case, the operator reported a brief but noticeable increase in handwheel resistance during the final turn, not enough to prevent closure, but enough to feel. Grissom placed his hand on the downstream pipe during the next closure. He felt a faint vibration as the valve closed, followed by warmth that lingered longer than it should have. The pipe surface was not merely hot from residual steam, it was being heated by steam that was still flowing or still present under pressure, even after the disc had seated. He considered condensation. Superheated steam, when trapped in a pipe and allowed to cool, condenses rapidly. The phase change from vapor to liquid creates a localized pressure drop, which in turn draws more steam from any available source. If the valve disc was seating, but not yet fully sealed, if there remained even a small gap during the final moments of closure, condensation downstream could create a transient pressure difference that resisted the disc's downward motion. But condensation, alone, did not explain the resistance felt in the handwheel. Grissom turned his attention to the packing. The packing gland, which sealed the stem where it passed through the bonnet, was tightened to prevent leakage, but not so tight as to bind the stem. During rapid closures, however, the stem heated quickly as steam flowed past the disc. Thermal expansion could increase the stem's diameter by a few thousandths of an inch, enough to increase friction against the packing. This stiction, static friction that must be overcome before motion can continue, could delay the final seating of the disc by fractions of a second. Combined with condensation forces acting on the underside of the disc, the result would be a valve that closed mechanically but resisted closure hydrodynamically. The delay was not a failure. It was a convergence of forces, visible only during rapid shutdown. Grissom drafted a memorandum in late January, summarizing his findings and proposing an explanation. He began with the observations. The valve closed mechanically in all cases, but steam flow persisted for several seconds longer during rapid closures than during slow ones. The handwheel required additional effort during the final turn of rapid closures. Downstream pressure decayed more slowly than expected. The valve body and stem showed no defects. He then outlined the forces he believed were at work. First, thermal expansion of the stem. During rapid closure, the stem remained hot from contact with steam. As the operator turned the handwheel quickly, the stem did not have time to cool. The increased diameter, even by a few thousandths of an inch, increased friction against the packing. This required additional force to turn the handwheel, slightly delaying the disc's descent. Second, condensation in the downstream pipe. As the disc approached the seat, steam flow decreased, but did not stop immediately. Steam trapped downstream began to condense as pressure dropped, creating a localized low-pressure zone. This pressure difference across the disc exerted an upward force, opposing the downward seating force applied by the operator. Third, pressure-assisted seating. Once the disc made initial contact with the seat, upstream steam pressure acted on the top of the disc, assisting closure. However, if condensation continued downstream, the pressure difference could momentarily work against seating, requiring additional handwheel force to complete closure. Fourth, stiction in the packing. The packing, compressed and heated, resisted the stem's motion during the critical final moments of closure. This resistance was not constant, but depended on how quickly the stem moved and how much thermal expansion had occurred. Together, these forces created a temporary opposition to closure that appeared only during rapid shutdowns under high pressure. The valve did not fail. It simply required more time and force to seat fully than its mechanical design alone would predict. Grissom proposed a modification, a packing design with lower friction and better heat dissipation, and a slight increase in the seating force by changing the thread pitch of the stem. These changes would not eliminate the forces at work, but would reduce their impact, allowing the valve to close more quickly even under transient conditions. The modifications were made in February. The valve was reinstalled and tested. The delay decreased, but did not vanish entirely. It remained measurable, 3 to 5 seconds under the most demanding conditions, but no longer troubled the operators. The valve was returned to service. The valve that closed too slowly was not broken. It was obeying the physics of its own closure, forces that only became significant when closure happened quickly, under pressure, during transient conditions. The delay was the result of multiple phenomena occurring simultaneously, each small on its own, but together sufficient to resist the disk's descent. Thermal expansion increased friction in the packing, requiring additional torque and delaying stem travel. Steam condensation downstream created a transient pressure difference that opposed seating. Stiction in the packing resisted motion during the critical final moments. Pressure-assisted seating helped eventually, but only after the disc had made firm contact, which itself was delayed by the forces acting against it. The valve worked. It always worked. It simply worked more slowly than expected, in ways that were invisible during routine operation, but unmistakable during emergencies. Engineers in the decades that followed would encounter similar behavior in other systems. Valves that resisted closure, pumps that hesitated to start, mechanisms that responded correctly but not promptly. The industrial age built machines that obeyed not only the intentions of their designers, but also the transient forces of heat, pressure, friction, and phase change. Some failures were not breaks. They were delays hidden inside normal operation, visible only to those who knew what to listen for. The valve at Belport remained in service until 1903, when the forge line was decommissioned. It was removed, cleaned, and placed in storage. No record exists of its final disposition. But the operators who worked with it remembered. They remembered the hiss that lasted too long, the warmth that lingered in the pipe, the resistance in the handwheel during the final turn. They remembered the valve that closed too slowly, and the quiet unease of a machine that worked perfectly, except when it mattered most.